Yeah, it's on.
Okay. I have the honor to introduce Khaled to you, who will give the third talk in our seminar series. He did his PhD at the University of Cape Town. Afterwards, he moved for his first postdoc to ANU, and currently he's working at the University of Queensland, and now he will tell us about his research there. Thank you. Go ahead.
Thanks, Christoph. Okay, so move not so fast. Just a second. Ah, sorry. I don't know why. Sorry. Okay. Sorry about that. So thanks, Christoph, for the invitation, and thanks for all the organizing committee. Thanks, David. Thanks, Ryan. Thanks, William. So it's really a great opportunity to give a talk at CASI, even if it's just virtual. And I hope like restrictions will ease like soon, and they'll be able to come and visit in person. So today we'll tell you something about like cosmology from Bikea velocities. And because all the talk is about Bikea velocities and cosmology, I will start first by introducing you to the state of cosmology today. So I'm gonna start by showing these two beautiful images of the universe. So on the left is the latest map of the CMB. And as you all know, we can only image the universe if it is transparent. And earlier than like 400,000 years after the Big Bang, the cosmic gas was sufficiently hot to be fully ionized, which means that atoms were broken into nuclei and electrons, and the universe was opaque due to the scattering of like by this dense fog of electrons. So we cannot use telescopes to image the infant universe at any earlier times. So, and this is the redshift of like 1,100. So, and what you see, like the red and blue dots shows you that density in homogeneity was at the level of 1 part in 100,000. So, and what does it mean? So it means that the observations of the CMB tells us that the universe was uniform in temperature to like 1 part in 100,000, when it was like several 100,000 years. So at early times, the universe was very close to homogeneous. However, if you look at to your right-hand side, so what you see like is all kind of structures, from planets to galaxy to superclusters. So like how that happened, how this transition happened, and this is one of the like the big questions in cosmology today. And the widely accepted view is that a small density fluctuation in the beginning grow by gravitational instability into all the structure that we see today. So basically, we can observe the universe when it was like only 400,000 years after the Big Bang, and we can observe the universe today. And we know exactly what happened in between, or we know the theory that govern what happened in between. So basically, we should be able to go back and forth and measure the same thing. So if we measure something like from the CMB map, measure some cosmological parameters, and we know what happened in between, so we can extrapolate and get the same results from the large-scale structure that we see today. Unfortunately, that's not the case. And we see tensions in many of our cosmological parameters. And the first one that I will show today is H naught, or the present day expansion rate, or Hubble constant. And I like this picture, like, because it shows that like you have a bridge, and if you take an early route, you end up in a river. And if you take the late route, you also end up in the river. So all the measurement from the late universe, or from like the low redshift, our own universe, the universe now, show you that like the measurement is centered around 37. However, if you take the early route, all the measurements is centered around like 67. Instead of 73, it's 67 now. And as you see, like the error bar is really, really tiny. Like from blank, like is really, really super tiny. It's not like fine tuning, or it's not reducing the error anymore. So there is something happening. So it's either some systematic error in our local measurement or in the CMB measurement, or it's something in between. So it's a signature of a new physics. And why we need a new physics? Because like to translate between measurement at early universe and like our universe today, you need some physics to go like back and forth. So this is the first tension that we see in cosmology today, but that's not the only one. So the second tension is in the sigma 8, and sigma 8 is the RMS density fluctuation on 8 megaparsec scale. So basically what you see here is a comparison between measurement from the CMB. This is an old map, our old constraint from the CMB in 2016. Should be updated now. So with kids and with other measurement, and one of the other measurement is the Soniev-Zaldovich effect, which is like also coming from Planck, but at low redshift. And you see like there is a tension, like all the low redshift measurement like is telling you something, and the high redshift measurement is telling us something else. And again, this is either a systematic error in the local measurement or a systematic error in the CMB measurement. Or like if both measurement, if we correct for all systematics in both measurements, this should tell us something or give us a hint about a new physics. The third tension, which like I think I will focus on this for the rest of the talk, is the F sigma 8. And F sigma 8 can tell us something about gravity. So we measure F sigma 8, and this F, we can it's the growth rate of cosmic structure, and we can parameterize it as a function of omega m and gamma is the growth index, which tell us something about gravity. For example, it's 0.55 for general relativity, and for another theory, it gave you another value. Like for example, here for the DGB, it's a weaker gravity, which gave a higher value of gamma of like 0.68. If you look at this plot was done by Faye, who's here today. And what they did, they took the measurement from the literature and their own measurement. So they take all the measurement and they put the green band, and the green band is a Planck measurement or the general relativity measurement with gamma equal 0.55. But when they saw this, they said, okay, this is not the best fit. Let's try and do a best fit. And when they did a fit and they fit gamma as a free parameter, they found a higher gamma, which means it is a weaker gravity here. So their gamma is like about 0.06, which is like a little bit weaker than general relativity. So now you have like all these tensions. You can say it's 3 tensions, or like you can combine them, say it's one tension. But the state of cosmology today is like in tension between low measurement and high measurement. So what can we do? What can we do to try to solve this measurement or try to correct for systematics? Actually, BQ velocity can do both. So BQ velocity can try to correct for systematics at low redshift measurements, and at the same time, it can directly measure some parameters, and it can tell something about the constraint some cosmological parameter. So I will start by introducing what BQ velocity is first. So any galaxy has 2 components of velocities. So they have the expansion velocity, which is always away from us, and you see it's this big arrows here. And they also have the BQ velocity. And the peculiar velocity is just the deviation from this smooth Hubble flow. So like the deviation from the expansion of the universe is the peculiar velocity. You can define it in another way by saying this. Okay, it's just a departure of the galaxy velocity from the mean value that's set by this Hubble law. So Hubble law is the relation between distance and recession velocity, and for each distance, like supposed to get a value for the recession velocity, and if you get more or less, this deviation is due to peculiar velocity. And now, because this peculiar velocity actually is a direct result of gravity, or like mainly gravity, so there is some other like peculiar velocity, like explosions, but we'll just focus on the ones coming from inhomogeneities or the gravity. And because it's a direct result of gravity, we can use it as unbiased tracer of matter distribution. So it's not only like we're tracing the luminous matter, but we can use peculiar velocity to trace luminous and dark matter. Okay, so now how do we measure peculiar velocity? So now we established that the peculiar velocity is due to an homogeneous mass distribution and not the Hubble flow. How do we measure it? So the first method is statistically. So we can measure peculiar velocity statistically using something called redshift space distortion. But if you want a direct measurement of peculiar velocity, you need something called distance indicator. And again, there's two types of distance indicators. There's a primary distance indicator, and an example for this is a Cepheid, tip of red giant, or masers. And as the name is telling us, it doesn't need any calibration from any other method. So it's just the primary as it is, it gives you distance. But it has a big problem. So it works only on a very, very low redshift. And for example, for Cepheids, even at 20 megaparsecs and with Hubble Space Telescope, you cannot go any farther than 20 megaparsecs. So you need to use something called secondary distance indicator. And actually, this has been actually the workhorse like that we use to get thousands of peculiar velocities. And an example of this is type 1a supernovae, Tully Floker relation, and fundamental plane relation. But again, the problem with this is you need a calibration from a primary distance indicator. So you need a calibrated relation like what you see in here. So it's like, this is an example of Tully Floker relation, which is an analytic relation between rotation velocity of a galaxy and the brightness or luminosity of the galaxy. And so once you have some galaxy with known distance, you can fit a model and use that model as the absolute calibrated relation. And you need apparent magnitude, and you need also some spectroscopic or radio observations as what you see here. I will explain it in detail. So basically, once you get the distance, so you can measure peculiar velocity using just the redshift. So this is a total velocity or the redshift. That's all what you get from the redshift. You get both of them combined. So it's not, so it doesn't differentiate between peculiar velocity and Hubble flow, and give you one velocity, which is the redshift. So once you get the distance, you multiply by Hubble constant and you subtract from the total velocity, you get peculiar velocity. So again, so it's called distance indicator. So it gives you distance, not peculiar velocity. And to get peculiar velocity, you need some cosmology, which is really bad. But I will show you like later how we go around this. So to explain this better, so I created this cartoons, which is first you select a sample of galaxy with known distance. So why known distance? Because you need luminosity on, you need luminosity on the y-axis. So you need to combine distance with apparent magnitude to get luminosity, and you need rotation, which is distance independent on the x-axis. So, and that's true for any other relation. So this is a Tully Floker relation. It's good because it's like 2-dimension. Fundamental plane, it's the same, but 3-dimension, I will show it later. But just for visualization, so it's, you need a distance-dependent parameter and distance-independent parameter. Once you do this, you try to fit a model to this with some intrinsic scatter of that model. So you fit this data, you get the model, and then you use this model as your ruler, the ruler that you will use to calculate distance for any other galaxy. So again, once you have this model, so you can select a sample of galaxy with unknown distance. So any galaxy, you can measure any galaxy, get some rotation, which is distance independent. You get some apparent magnitude, which again, distance independent. And from the rotation and the model, you can read the luminosity. And by comparing luminosity to your apparent magnitude, you can get distance. So this is how you get BQI velocity from the distance indicator. So once you get this, if you want to get some cosmological parameters, you need a model to compare with, and then to say, okay, does my data agree with this model or not? And you try to fine tune. How do we get this model? And we get this model from something called Reconstruction. And it's called Reconstruction because it tried to reconstruct the real universe from the redshift universe, or like try to reconstruct the velocity and density in real space from just the redshift. So the first thing that you do is you try to find the fluctuation in the density itself by using this equation. So this is not density, this is a fluctuation in the density, and that's why you can see it goes to minus. And like if it's density cannot go to minus, but the fluctuation itself can go to minus. Once you have this fluctuation, the integral over this fluctuation of density can give you the velocity. But if you look carefully, this is the total fluctuation in the matter density. So it's not just the galaxy density, but it's in the total matter. And to account for this, we use delta G. So it's a fluctuation in the density of galaxy survey, not the total matter. And we use delta G instead of delta, and we just add another parameter called P, which is a bias parameter. Which is the difference between, it tells you something about the difference between the galaxy distribution and the total matter distribution. Another problem in this equation is that it cannot go forever. And for any integral, or specifically for that integral, you want it to go from 0 to infinity, but we cannot observe the whole universe. So we cannot go to infinity, so we cut our integral at a specific point, say 200 megaparsecs, and we add this another term, which we call V external, which is the bulk flow or the velocity due to any contribution outside of our survey. And we fit it as a free parameter. So again, we remove this f over b, and we put it as beta, and we want to remove b because we don't know anything about the bias. So we use, instead of sigma 8, we use sigma 8g, and sigma 8g is just a bias multiplied by sigma 8. So instead of the RMS fluctuation in the matter density, the total matter density, we use the galaxy survey to do this. And this can, it's a very easy measurement. You can do it using a galaxy survey, using a count in a cell. And then your f sigma 8 now become beta sigma 8g. So you fit beta, and you get sigma 8g directly from the Redshift survey, and you have a velocity here. But we don't want to use any cosmology. So what we do is we normalize. We use beta equal 1, and we put V external equal 0 for a moment, and then when we compare, we measure the cosmological parameter that fits our survey. And that's, again, I created this cartoons. So you have two velocities now, and we call this process velocity-velocity comparison. So the first velocity here, or the measured one, is the one that you get from Tully Fisher or fundamental plane directly. And the predicted one is the one you get from the model, the one you get from here. So, and again, this is an all normalized. So we don't know what's F over B. We don't know what's V external, and we fit them. F over B, we call it beta, and V external, like you get a value for V external. This is just a cartoon. So for V external, it's a vector. So it's you get Vx, Vy, and Vz. Okay, so now you know like the state of cosmology, and you know how to get BQF velocity, and from this BQF, how to use BQF velocity to get some cosmological parameter. So I will move on to like what we really did. And before going ahead, there's a very important slide introducing the team, so they can like share the glory with me, and also share any other mistakes in the paper. So I used to work at ANU with Matthew Collis, and we had like one of the team was Christina Magoulas, which she used to be like Matthew's student, but she's now working in the Australian synchrotron. And we also have on the team, we have John Lucy from Durham, and we have Mike Hudson from Waterloo. And they did a lot of work, and like that was like a great team. And this is like we were working on the paper when we were at the Cosmic Flow conference in South Africa, and I think Christoph was in that conference with us. So here in that paper, we didn't use Tully Fisher. Instead, we used fundamental plane relation. And fundamental plane relation is very similar to Tully Fisher, but in 3D. So you have RE, which is the radius of the galaxy, which is the only distance-dependent measurement in your relation. And they have velocity dispersion of stars inside the galaxy. And this is not the velocity dispersion of the galaxy inside the cluster. Instead, it's like the velocity dispersion of the galaxy. And you have IE, or like the mean surface brightness. And you have A, B, C is the free parameters that you want to fit. So for the effective radius, which comes from the photometry, so the error is about 2% for 6DF. And for velocity dispersion, this is the dominated error, which is like 12% error. And for the mean surface brightness, which comes from photometry, it's 3%. And for photometry here, we use 2 mass, J-band specifically. And for the spectroscopy, we use the selected J-band 6DF sample that was already published by Lachlan Campbell in 2014. So you combine all of them, and you get an estimate of the error on the distance error, which is like directly correlated to the error on sigma r in the direction of the r direction, and we get something about like 31% error. And this tell you this, we cannot use 6DF at very high redshift, because the error can be like very high. So it can be even higher than the BQF velocity itself, because it's 31% of the redshift. So it's most of the time it is higher than the BQF velocity. So we don't want like to go very far. We need to use it just for the local universe. So that's the first survey. The second survey is this SDSS survey. And we saw a problem in SDSS, like when we first looked at the data, and we tried to look at plate by plate. So as you know, like SDSS was observed on plates by plugging the fibers. So, and if you look at the galaxy that was observing on this for the same galaxy, but on multiple fibers and on like different plates, we saw actually a systematic difference. And we calculated a systematic difference of about 4%. We saw that it can give us a BQF velocity of 45 kilometers per second for a galaxy at distance of only 8,000 kilometers per second. So this is really huge. So the value of BQF velocity is always around like 300. So if you get an artificial signal of 450, this is a killing signal. So we try to look at this like more qualitatively. So by doing this pool distribution, and pool distribution is like taking just the velocity dispersion, taking the velocity dispersion from the primary plate minus the secondary plate divided by the square root of the quadratic. You add the error in quadratic. And you see that this is supposed to give you a Gaussian with a mean of 0 and sigma or standard deviation of 1 if it is not biased. So if there is no plate-to-plate offset, this should be the case. So what we found a slight, like a very tiny offset. So I agree, it's a very, very tiny offset. And sigma was like 1.14 again. So it's like a slight difference. But what worries us more is this like flat top of the Gaussian. So we tried to correlate this, what we see, with any of the other parameters, so like from right ascension, declination. So maybe when the telescope moves, so the position like change, and that might end up like giving a lower signal to noise, which affect the measurement of velocity dispersion. But that's as you see, that's not the case. We don't see any correlation with RA and DIC, or even with seeing, or like even with signal to noise. So you see here, even with signal to noise, there is no correlation. So we got all the raw data and we tried to analyze it ourselves. And that's what we did. And that's what we found. So like if we take the pipeline data from SDSS, that's what you get. If you measure your own velocity dispersion for all of them, the secondary and primary targets, so you get this pretty Gaussian with like even less offset and even near like to 1 standard deviation. So we were like very happy with this distribution. We said, okay, we should go ahead and like try to do some cosmology with this. So the first thing that we did, so we did the same as what we did with 6DF, we did with SDSS, and as you see, the photometry again gave us like 2% error on the effective radius and 3% error on the mean surface brightness. And it was much better than the velocity dispersion, like error was much better than 6DF. So 6DF, it was like 12, here it's 7%. I put them side by side now. But just to look here, so it gave us like 24% error instead of 31. So if you look at them like side by side, that's what you end up seeing. So spectroscopy is a killing factor here, and it moves you from 31 to 24%. So we used both survey together, but we'll move like, so each survey, we'll do each survey separately. We'll not combine all the surveys. So we fit the fundamental plane for all galaxy, and for 6DF, we have about 9,000 galaxies, and for SDSS, we have about like 25,000. But this 25,000 actually goes to 0.1, which was a problem for us because we don't have reconstruction at 0.1. All what we have is like 0.06 or something. So we did cut the survey to the same redshift as 6DF, and we end up with like about the same number. We end up with 9,000, the same as 6DF. So, but again, so we didn't do the 2 steps. So we thought, okay, instead of doing calibration first and then we do the distance, so we'll do everything at the same time. We'll not even calculate distance. We'll marginalize over distance, and we'll try to get just cosmological parameters and fundamental plane parameter. And if you look at the likelihood, if you're at the likelihood, this is just the fundamental plane. This is the observable. This is the predicted. And this is like some distance that we marginalize over. And this term actually is the most important term, is where you combine the observable with the model and all your cosmological parameters in here. And this is just a probability. The last term is just a probability of observing that galaxy at that distance given your density, which like kind of correcting for Malmquist bias here. So once we do this, so we get this beautiful pairwise joint constraint on A, B, C, and sigma, which is the fundamental plane parameters. And you also constrain beta, Vx, Vy, and Vz, which is the velocity model. And again, what we used here is like what you see in red is the 6DF, what you see in blue is the SDSS, and inside this calculation is a 2m++ catalog normalized to have no cosmology. So if you download the 2m++ model, it already has some cosmology in it, but you can normalize this to remove beta, any beta and V external, and just like fit your own beta and V external. Okay, so if you look back here, so before moving, so we found beta actually that was like a little bit low compared to like lambda CDM. So the first thing that we thought about is like maybe there is some redshift dependence in our measurement that might be the like biasing our beta. What you see here is a fitted 6DF, not SDSS, only 6DF beta values in shells of redshift. And the number of galaxy moves from like 600 here to 1,000, 2,000, 3,000. And as you see, the error bar is almost the same, like because when you go to redshift, your error on the distance is higher. So like it cancels out. And if you look, there is a trend somehow, but it stopped. And it is also consistent with our final measurement from the 6DF. So this gray shaded region presents the overall beta value from the 6DF. So we think it's not a redshift dependence. It is what it is. So our value is like lower than the lambda CDM. So this is that was for beta, and this one is the distribution of all the 16,000 elliptical galaxy in 6DF in red and SDSS in blue. And this is a color coded basically by Redshift. And if you look carefully, you will see here, so a circle and a star. And this circle and the star is the direction of the external bulk flow that we measure from our own sample. And they agree very well with each other. And it happened that they agree also with previous measurement. And this measurement was like completely independent. So for Borwa, they used supernovae, not fundamental plane. And for Carrick, they used Tully Floker. And this is like two independent samples. So the only like dependent step in this in the four measurement is a 2m++ catalog. But again, our 2m++ is normalized, so it doesn't have any cosmology. And it happened that our measurement is exactly between Vela supercluster, which is as a triangle, and Shapley supercluster, which is the square over here. But it is inside the zone of avoidance where nobody has any data, so we don't know like what's in there until we actually observe there. So now into some cosmology, and the first thing that we do is F sigma 8. And if you look here, so this is a constraint of the growth rate of cosmic structure of our 6DF, the red, and blue is SSS, and combine them is a green one. And if you look, it is well below the model, and this is all this models is blank models with only changing gamma. Gamma is a growth index, which tell us what theory of gravity it is. But if you look carefully, also like it's not only us. So almost everyone gets a measurement that's lower than the model that's set by Planck measurement. So that's what Fay found in 2019. So instead of fitting a model to this data, what we did is we tried to fine-tune this model. So if you fine-tune this model to have H naught of 74, which is the current low measurement, and from the 2-point correlation function, you get omega m and sigma 8, and you use omega m and sigma 8 to plot these models. And you see it's a much better fit to our data and all the other data than the values that was set by Planck. So that was the first indication for us. And the second thing, we tried to fix the values of Planck. So we leave Planck measurement the same, but instead of changing gamma, we change sigma 8. So we keep omega m, which is Planck value, but we change sigma 8. And if you look, so you need a very low value of sigma 8 to live in the universe that's like set by a Planck measurement. So like, and if you think about sigma 8 is just the RMS fluctuation in the density or at like a sphere of 8 megaparsecs. So if you take many spheres in the universe and take the RMS of them, like it has to be like very low, like 0.6, which means that the universe is like didn't create that much like clumpness of matter still, or didn't have much time to create that clump of matter. So say again, Christoph, please.
10 minutes.
Okay, thank you. Okay, so in general, our conclusion for this is our measurement our like surveys need a gross index bigger than the value set by generativity, which like means bigger than 0.55, or a Hubble constant higher than 70, or sigma 8 less than 0.8, or some combination of all of the above. So we need to try to fine tune until we get the universe that describe our data. So we can do actually something else. We can do a model dependent sigma 8 directly from our measurement. So if you assume gamma of generativity and you take an array of omega m, and for each gamma and omega m you calculate f, and you already have f sigma 8 from your measurement, so you calculate sigma 8, and you see here, so our sigma 8 is a green one here. So this is just S8, just a normalization of omega m. So if you look at sigma 8 against omega m space, you look, and our measurement agree with kids and within 1 sigma, and it also agrees with like this with 1.5 sigma, but it really deviates from the Planck value, which is the blue tiny contour here. So that was our conclusion. So again, so the tension still there, and it's even stronger than what we think. And we need to think carefully about how to do things at low redshift and at high redshift. Or if we think there is nothing wrong that we're doing, I think we need to start thinking about some new physics. Okay, so that's what we did. So I will go like very quickly on describing some current and future peculiar velocity survey that we're doing, that I'm included in. So the first one is creating SDSS peculiar velocity catalog. That project is led by Cullan Howlett. So what we're doing, so we're building on what I did for my project, but we go in further in redshift. We go into a redshift of 0.1, and this time actually we fitting distance. So we calibrating, we go in the 2 steps. So we calibrating the relation, we setting the 0 point, and then we measuring so we calibrating the relation, we measuring distance, and then we setting the 0 point. And because we don't need any reconstruction for this project, so we went to 0.1 instead of 0.05. So if you look here, here's a distribution of SDSS PV data in blue, in a galactic coordinates, obviously. and we're comparing it with SDSS, which is red ones, and the all cosmic flow 4, which is like about 10,000 galaxy, which is the green dots. And you see it's like, so our number is about like 30,000 BQ velocity galaxy after removing all the galaxies that we think it's not ellipticals. So it should be much, much better than any previous survey. And if you look at the number density, so this is a redshift distribution of the SDSS BQ velocity sample again, compared to data from 6DF and cosmic flow. And you see it's like, especially at high redshift, it is the only BQ velocity that we have now. So this is the first project. The second project is led by my student, Rianna Bell. She's working with me and with Tamara Davis. So we're calibrating the Tully-Fisher relation using a new WISE data. And she is using the biggest sample that ever used to calibrate Tully-Fisher relations. She is using about 900 Tully-Fisher galaxies. And if you look, this is just the raw data. And this is after she did all kind of completeness bias and morphology. And I don't know if you can see difference, but like I can tell you, it's much, much better than the raw data. And she already established some results. And this is a Hubble diagram over here. The third project, which is led by Rafif Rabbani, who's like a student with Matthew Collis and myself at ANU. And and Rafif is doing things differently. So Rafif is taking all 3 surveys. He's taking 6DF, SDSS, and LaMost. And instead of like driving cosmology from each one of them, Rafif is doing something very, very smart. He's combining all the survey from the very low, at the low level. So using the same photometry for all the surveys, the same selection function, and then he tries to bring the spectroscopy to the same 0 point. So basically, he's trying to find pairs between SDSS and 6DF, pairs between SDSS and LaMost, and again 6DF and LaMost. And he tried to do this process iteratively until there is no offset, so the offset is 0 and the standard deviation is 1. This is a very, very promising project, and this is a future project. So Wallaby, Daisy BGS, and Foremost. Wallaby is a H1 survey happening here in Australia, and it will give us about like 30,000 distances of Tully-Fisher distances. And the forecast telling us that it will be like 3.7 error on F sigma 8. The survey already started. Like we have data from 3 pilot surveys, and the full survey should start soon. And Daisy BGS, which is like me and Christophe are included in, and Christophe did all the selection for the galaxies. And we can use Tully-Fisher and fundamental plane for like with Daisy, because they have multiple fibers, and we can space the fibers along the major axis and minor axis. We can get some rotation curve for the Tully-Fisher, and we can get some velocity dispersion for fundamental plane. And this will give us like about 50,000 just big galaxy when we space the fibers, and it can give us like about 250,000 fundamental plane galaxy, which is like will be great. And the survey already started, and we have some data. We just need, me and Christophe need to go and look at the data that we have. And the third survey, which will be the most promising one, but still proposed. So if this survey is approved, it will give 500,000 fundamental plane galaxy. And if it starts, if it's approved, it will start by the end of this year, and it will be able to get the data right away. So I will end by this beautiful image about the future of BQ velocities. And if you see, that's all what we have at the moment. So what's in the center is all what we have at the moment. And with Daisy and for HS, it will look completely different. So thank you. That's all what I have.
Thank you very much for this very interesting talk. So any questions? Okay, if there are none, I will ask a question. you said that with Cepheids, currently we can only go to around 20 megaparsecs. Are there
Yes,
any
that's correct.
estimates how far we could go when we have the James Webb Telescope?
I'm not sure. I've never measured distance with Cepheid myself, but I think it will still be very hard. So Hubble went like very deep. So it's not that Hubble was shallow. No, Hubble can get you a very deep imaging. So I don't think if anyone can do a Cepheid measurement with any telescope or like even a future telescope that's with a distance higher than 20 megaparsecs.
Okay, so sadly no advances there in the near future. Okay. um, then anyone else questions?
I have a question.
Yeah.
In the velocity comparison method, for the measured velocity, they are measured from the galaxies, they are point source, but the reconstructed velocity field is in a grid. So how can you compare galaxy velocity to a grid grid cells?
Yes, that's really a great like question, and it's something that we like different groups cannot even agree on. So what we do with the density, so you take the density and you basically smooth, and you get the velocity, which is smoothed at some level, like say 4 megaparsec, and you compare it with like unsmoothed velocity, and this should give you a biased result. And actually, there's a great paper. I can't remember the name of the first author that shows exactly like what the bias you see. And what we do, we try actually to try to have some marks, and we try to smooth, like we go from like 1 megaparsec to 10 megaparsec and try to see like if when we compare. So for the marks you have the velocities and you know the true velocity, and you can compare. So we move, so we have a mark that describes your survey, and you do the density, you smooth, you get the velocity, and you try to compare different smoothing until you get the best smoothing that gave you the best results. It gave you one-to-one results instead of like washed signal. So if you smooth like at very high scale, like 8 megaparsec or 10 megaparsec, you might get a washed signal. So if you put the predicted on the x-axis, it will look like this. So it will not be one-to-one line, but will be only a horizontal, a vertical line, because all the signal is washed. So we try to get the best smoothing length that we should use before doing this comparison.
Okay, thank you. Any other questions? While you think about them, I have another question. So since you did work with both the fundamental plane and the Tully-Fisher relation, did you notice any systematic differences also on when you use it as cosmological probes? Because fundamental plane statistically probes more the clusters and the Tully-Fisher relation more the field.
Yes. So like, is your question, is there a difference?
Anything that's different systematically between the two indicators?
So not really. So like if there is anything, it will be just a redshift. So for Tully Fisher, actually, you cannot go like very far with redshift with Tully Fisher, because you lose all the spiral arms. So you get only the bulge. So like you stop Tully Fisher, like the highest Tully Fisher is like 0.03 or 0.05, while for the fundamental plane you can go like as much as you could. But I personally, like, I didn't find any difference in the measurement. So all the measurements from Tully Fisher and fundamental plane was pretty consistent, like at the very high end, like I mean like cosmology end.
Okay.
So and I think Christina Magoulas and Matthew Collas, I think they tested this like thoroughly in their paper, if they are biased because they observe only galaxy in the clusters. I think in Christina's 2012 paper, I think they tested this and they found that there is no bias.
Okay, good to know. Yeah. Any other questions? Okay, if not, we can thank the speaker again. David, you can stop the recording and